Hello, today we are going to start our new lecture on thin films depositions through gas phase techniques. If we remember that in my last previous lectures also we have discussed about some gas phase techniques, but here in this particular lecture we are going to discuss some advanced gas phase techniques which we are going to use for the modifications for the surface. So, first, before going to start, just we have to know little bit about the gas phase deposition techniques. So, as we know that there are several types of deposition techniques which is called the solid deposition techniques, where generally solid phase deposition methods we are going to use, like the diffusion process. Then we are having that liquid phase deposition method which apply chemical reactions in the solvents, and when you are talking about the gas diffusions means we are doing this kind of modifications into the gas phase itself. So, in gas phase deposition process, precursors were deposited onto the substrate via gas phase. So, first I am having that precursor or maybe the target materials, then I am having the substrate materials. So, I have to heat it or maybe some other means I have to create some kind of vapor or maybe the gas, then that vapor or gas will directly go and it will deposit onto the material surface. So, most depositions of thin film of nanoparticles in the gas phase are based on homogeneous nucleations in the gas phase, subsequent condensations and the coagulations. So, generally this is the standard method by which we are doing the gas phase depositions. So, from this particular case we can understand that we are having that thin films, we are flowing the gas on top of that. So, from that gas phase the molecules is coming, then first the absorption of this film precursor is taking place onto these ones, then some kind of volatile gas it is removing from that particular substrate, and then the pure molecules is attaching with the surface, then they are doing the reactions, then nucleations of the growth is taking place, and some kind of volatile surface or maybe the toxic gas it is removing directly coming out from the material surface, and by one layer to one layer the step growth mechanism, by step growth mechanisms the film depositions is taking place. So, now we have to discuss about that several types of classifications of the gas phase techniques. So, as I already told, there are several types of techniques generally we are following. So, one is called the chemical vapor depositions, in short form generally we are calling it as a CVD process. Then atomic layer depositions, ALD process, molecular beam epitaxy MBE process, thermal nitridations TN process, thermal oxidations is TO process. So, there are more or less 5 different methods by which we can do the gas phase modifications of nanomaterials. So, first let us know that what is the chemical vapor depositions, that means main approach for fabricating the thin film using the gas phase. So, as I already discussed that chemical vapor depositions that we have already discussed in our last lectures, means lecture number 13, as its name implies, it involves a gas phase chemical reactions occurring above a solid surface which causes deposition onto the surface. So, if you remember that here we are using different kind of vapors, that suppose the vapor of methane, vapor of hydrogen, then they are going and they are reacting on the substrate and they are forming a new material on top of that. So, by this here that generally we are following some kind of chemical reactions. So, that is why it is known as the chemical vapor deposition process. Next we are going to discuss about the atomic layer deposition process. So, atomic layer deposition is also well known for depositing confocal and continuous film onto structures having very high aspect ratios. So, here also we are taking different kind of precursors. So, either we can take a single precursor, we can take multiple precursor, then they will react each other, then they will form some kind of molecules, then that molecules can directly go inside the substrate itself, or maybe they can make a layer by layer onto the surface side. So, by this one we are doing the atomic layer depositions of these particular molecules or maybe the atoms. Then next one is that molecular beam epitaxy it is also a one kind of gas phase deposition methods. Before going to start about the molecular beam epitaxy, just let us know that what is it actually. So, it was invented in the year 1960s at Bell Telephone Laboratories by J.R. Arthur and the Alfred Y. Cho. So, from the year you can understand that it is not the newer method, it is little bit the older method, but still this is the good method which we can follow. It is technique for epitaxial growth via one or more molecular or atomic beams that occurs on a surface of a heated crystalline surface. So, generally we are taking it as a heated crystalline surface, then top of that we are growing the layer by layer techniques, we are doing the modifications by layer techniques, and that is known as the epitaxy film. So, here the term means the evaporated atoms do not interact with each other or with other vacuum chamber gases until they reach the wafer. Ultra pure elements are heated in separate quasi-Knudsen effusion cells like gallium and arsenic until they begin to slowly sublimate. Gaseous elements then condense on the wafer where they may react with each other to form the thin films. So, from this particular figure we can understand that here we are having the substrate, then we are having the dopant, gallium, arsenic, aluminum and the dopant itself. So, here this is one kind of gun. So, I am having the substrate from where the dopant is coming, then it is giving a layer onto the substrate, then gallium is coming, it is giving a layer onto the substrate, then arsenic is coming, it is giving a layer on the substrate. So, any kind of combinations of the surface we can do by this kind of molecular beam epitaxy. And here from this particular figure you can understand that first we have given the arsenic film over there, then we are putting the gallium film over there. So, growing the epitaxial layer one by layer it is forming, and then when they are reaching onto the substrate then only they can react with each other, but when we are allowing them to go up to the substrate, before that they are not reacting each other. That is the beauty of these particular techniques. So, now we have to know what are the working conditions for the molecular beam epitaxy. So, the mean free path of the particles should be more than the geometrical size of the chamber, 10 to the power minus 5 torr is sufficient. Yes, it is quite natural. Suppose I am having that substrate in this particular range, and if my molecules free sample path is less than that. So, what will happen at the time of vapor or maybe the gas, it will not directly reach onto the wafer itself. So, its mean path should be more than the distance in between the target material and to the substrate material. Next, ultra high vacuum, generally UHV is equal to 10 to the power minus 11 torr, we are telling it, to obtain sufficiently clear epilayer. Gas evolutions from materials has to be as low as possible. Pyrolytic boron nitride PBN is chosen for crucibles, chemically stable up to 1400 degree centigrade. Molybdenum and tantalums are widely used for shutters. Ultra pure materials are used as shores. So, these all are the working conditions for these particular techniques. Now, we are going to discuss that there are also the classifications in between the molecular beam epitaxy methods. What are those? First one is called the solid source MBE. So, group 3 and group 5 molecular beams for 3 to 5 semiconductors, just a combinations of indium, gallium and arsenic. Group 2 and 6 molecular beams for group 2 to 6 semiconductors like Hg, Cd and tellurium etc. Plasma assisted molecular beam epitaxy, group 3 molecular beams and nitrogen plasma source for nitrides is a combination of aluminum, gallium and nitrogen. Oxygen plasma or atomic oxygen source for oxides, that means magnesium, zinc, oxygen, zinc oxide or maybe the titanium and the titanium dioxide. Reactive MB, group 3 molecular beams and ammonia gas injector for nitrides like aluminum, calcium and nitrogen, ozone gas injector for oxides. So, that is the thing is that what is the target and what is the gas phase I am going to use actually. If my target material is totally solid, then it is known as a solid beam epitaxy or maybe that solid molecular beam epitaxy. If we are using that materials into the plasma form, then it is called the plasma assisted MB, and if we are using certain kind of materials, then when it will reach touch with the wafer, it will react, or maybe before when we are agitating that materials, maybe they can react and they can form a new materials. So, that is it's why it is called the reactive molecular beam epitaxy. So, now we have to know that what are the advantages and disadvantages of this particular process. So, advantages is that we need the clean surface free of an oxide layer, otherwise whatever the material we are generating, when that will deposit onto that substrate itself, it will not do the proper adhesions. So, after certain time that layer may come out from the substrate itself. In situ depositions of metal seeds, semiconductor materials and the dopants, low growth rate, precisely controllable thermal evaporations, separate evaporations of each component, substrate temperature is not high, ultra sharp profiles. So, these all are the advantages for these particular techniques, but of course, there is certain kind of disadvantages too. First of all, it is very expansive process, okay. Then very complicated systems, epitaxial growth under ultra high vacuum conditions. So, these all are the different types of disadvantages of this particular process. Applications. So, generally we can make some kind of novel structures as quantum devices, silicon insulator metal sandwiches, super lattices, microelectronic devices. So, mainly the application is all the electronic based applications, but some other applications also we can do this kind of coatings. Next one is called the thermal oxidation process. So, in the name itself, thermal oxidations means we are using certain kind of heat energy to agitate the materials and by which we are doing the coating. So, what is the definitions? A process to grow high quality silicon dioxide film by thermally oxidizing silicon in oxygen containing ambient. So, simply we are taking the silicon wafers over there, then we are heating that silicon wafers into the oxygen environment, so that silicon atoms and the oxygen they can react each other and they can form the silicon dioxide, and that silicon dioxide directly we can deposit onto our substrate. So, thermal oxidations of silicon is usually performed at a temperature between 800 degree centigrade to 1200 degree centigrade, resulting in so called high temperature oxide layer HTO. It may be used either water vapor or molecular oxygens as the oxidant. Either we can put the oxygen gas over there, or maybe some kind of water vapor we can put inside the chamber itself, and here hydrogen is nothing but the carrier gas. So, for example, formation of the silicon dioxide film by the thermal oxide layer. So, here we are having that oxygen atoms, we are having that SiO2 molecules, then SiO2 molecules is getting reacted with the oxygens and they are forming the silicon dioxide on the substrate itself. So, oxides are grown by generally by three methods we can generate this oxide into onto the substrate itself. So, first one is called the dry oxidation process, where generally hydrogen and oxygen were introduced directly into the oxidation furnace. So, the reactions looks like this: silicon is into the solid form plus oxygen, it is forming the silicon dioxide at the high temperature. Wet oxidation process. So, here the oxygen we are using as a gas and that is the dry one, but when we are talking about the wet oxidation process, generally we are using the water vapor over there. So, high temperature in tube forms stream. So, what is the reactions? Silicon solid plus 2 water is equal to, it is forming the silicon dioxide solid form and 2 hydrogen gas at high temperatures. But when we are talking about the chlorine oxidation process, simply we are replacing the water vapors and instead of that we are putting the hydrochloric gas inside it. So, then the reactions is coming like that: silicon plus HCl plus oxygen forming silicon dioxide plus hydrogen plus chlorine at high temperature. So, these all are the different process by which we can do the thermal oxidations. So, from this particular figure you can understand that we are using this kind of techniques for the electronic purposes. So, like MOSFET, like CMOS, like FET, some kind of graphene, CMOS photonics, there are the lots of applications where we are using this kind of thermal oxidation process. Here one is the examples that where if we go for the year to year like 1989 to 2004, the thickness of the materials, how we are reaching into the nanoscale size, means the growth of that layer is very fine onto the substrate itself. and here this is the reactions which I was talking about. So, we are having the silicon surface, then that silicon it is generating the Si ions, and then we are adding some kind of oxygen gas and the water vapor or maybe the simple hydrogen gas, they are reacting each other and they are forming the silicon dioxide layer on top of the wafer or maybe the substrate. So, here this is the overview of the thermal oxidation process. So, first step, generally we are wet clean by chemical process, by solutions, by temperature or by time. So, we have to clean the surface itself, then we have to put the material into the oxidation furnace in the atmosphere of oxygens, hydrogens, maybe nitrogens or maybe the chlorine. Flow rate we have to maintain, exhaust we have to keep it, then we have the options to increase or decrease the temperature, because maybe sometimes depending upon the temperature various chemical reactions is taking place, and then we have to keep the time over there. Then last one is called the inspections, where we can check the film thickness, uniformity, particles, and if there is any defects onto the substrate or not, whether the coating is homogeneous or heterogeneous or not, or maybe that layer thickness is continuous throughout the surface or not. Then effect of oxidation rate depends on the thickness. So, this is one kind of literature review results. What we have found that the thermal oxidation rate slows with oxide thickness. Consider a silicon wafer with a patterned oxide layer. SiO2 thickness is generally 1 micrometer. Then silicon, now suppose we grow 0.1 micrometer of silicon dioxide thickness will be at that time 1.02 micrometer, and here the silicon dioxide thickness will be 0.1 micrometer. Note that the 0.04 micrometer step in the silicon surface. So, as the oxide layer formations will be increasing and increasing, so automatically by normal logic that silicon whatever is coming from the silane or maybe the wafer, that quantity will be less. So, automatically the reaction will be also reduced. So, automatically the oxide formation will be going to be decreased. So, then the thickness, growth thickness is also will be into the decreasing manner. Next one is called the thermal nitridation process. So, direct thermal nitridation using nitrogen gas, ultra thin silicon nitride films were found to be formed only under ultra high vacuum conditions. So, here generally we are doing the nitridation process. Last lecture we are discussing about the oxidation process, here we are doing into the nitrogen atmosphere itself. So, here how we are doing, we are taking the silicon nitridation is prepared by heating powdered silicon between 1300 degree centigrade to 1400 degree centigrade in an atmosphere of nitrogen. Just here we are replacing the oxygen gas, we are replacing the hydrogen gas, and we are introducing the nitrogen gas. That is why this process is known as the thermal nitridation process. So, here we are taking the silicon then with the nitrogen and we are forming the silicon nitride materials. So, silicon wafers could react with nitrogen molecules to form silicon nitride films on the surface of silicon wafers. So, here this is the schematic diagram of direct thermal nitridations of silicon wafers. So, we are having the nitrogen cylinder, then we are having some flow meter by which we can control the flow of that particular nitrogen inside the chamber itself. Then we are having that silicon wafer, simply that nitrogen is going into the quartz reactor, then we are keeping it into the vacuum pump, so that inside is the vacuum. Then we are putting the whole reactor onto the furnace, so that we can increase or decrease the heat on the substrate. Then the nitrogen is reacting with that surface and they are forming the silicon nitride. So, this is the growth curves of the direct thermal nitridation of silicon wafers. So, if we increase the nitridation times in minutes, so automatically we can see that thickness is also increasing. So, here we have seen that at two temperature how the growth mechanisms is taking place. One is called the 1100 degree centigrade, another one is called the 1200 degree centigrade. So, growth of thin films is enhanced by a flat growth mechanism after an initial rapid growth. So, simply if we keep that experiment for a longer time, so automatically our thickness of that coating will be automatically increased, and then silicon nitride films are denser and good diffusion barriers than the silicon oxide films. This is the added advantage for the thermal nitridations over thermal oxidation process. Benefits of the gas phase techniques. So, there are lots of benefits, generally we can get it by these techniques itself. What are those? First one is called they can be deposited with very high purity. So, here the incorporations of the impurity is very less. Then relatively high deposition rates, because it is controllable. It depends upon the gas flow rate, it depends upon the target materials, it depends upon the how much energy I am putting onto the target material. So, it is totally under control. Then good reproducibility, that means if the same sample I am doing it today, and if the same sample I can do it tomorrow also, whatever the properties in terms of thickness, layer, homogeneizations, everything, it will be almost same. So, that is why it can reproduce the same results in future also. Can grow the epitaxial film by layer method, it can grow onto the substrate itself. Thickness control at atomic scale, already I have discussed that thickness control is very controllable by these methods. Superior conformability and the wide range of materials can be deposited, more or less any materials which we can put into directly into the vapor or gas phase, that material can be easily taken out and can be used for this particular purpose. So, here these all are the schematic diagram already what we have discussed till now. So, schematic of MB setup, then experimental setup of the chemical vapor deposition process, schematic presentations of the atomic layer deposition setup, experimental setup of the thermal nitridation process, and the last one is the experimental setup of thermal oxidation process. So, it is giving you a more or less the glimpse about the whole lecture. Then we have to discuss, because till now we are discussing about the different deposition techniques. Now we are discussing that how the film is forming onto the substrate itself. So, the derived flux equations from the Fick's law, flux of the material F1, diffusion flux of reactant species to the wafer through the boundary layer is equal to mass transfer flux. So, here we are having that silicon, on top of that we are doing the coating. So, this is called the boundary layer by which we can grow the film onto this wafer itself. So, the famous equations calling it as a Fick's law, that is F1 is equal to Hg in the first bracket Cg minus Cs. So, where H is the mass transfer coefficient in centimeter per second, Cg is the reactant concentrations at bulk of gas, Cs is the reactant concentrations at substrate surface, F2 flux of reactant consumed by the surface reactions, surface reaction flux F2 is equal to Ks into Cs, where K is the surface reactions rate in centimeter per second. In steady state, if F equal to F1 is equal to F2, after equating we can get Cs is equal to Cg into 1 plus Ks by Hg to the power minus 1. So, by applying this law we can easily get the film growth rate of that onto the substrate itself. And before going to know that the film growth rate, we have to know all these values. So, simply we have to take all these values, we have to keep put into this all these equations, and automatically we can get the film growth rate. So, depending upon that we can increase or decrease the gases flow rate, or maybe that energy what we are applying for the target itself. So, there are lots of input parameters by which we can easily control the film growth rate onto the substrate itself. Now, the growth rate of the film is now given by the equations is called the V is equal to F by N, which is nothing but the Ks into Hg divided by Ks plus Hg into Cg by N is nothing but the Ks Hg Cty by Ks plus Hg into N, where N is the number of atoms per unit volume in the film itself, Y is the mole fractions, partial pressure by total pressure of the incorporating species, Ct is the total concentration of all molecules in the gas phases. So, if that Ks is lesser than the Hg, then we can obtained surface reaction controlled case, that is V is equal to Ct by N Ks Y. If Hg is less than the Ks, then we have the mass transfer or gas phase deposition control case, where V more or less equal to Ct by N into Hg Y. So, this is the equations over there. So, here this is the mass transparent limited regime and this is the reaction rate limited regime in terms of temperature, and this one is the diffusion rate in the logarithmic form. So, here first the mass transport is taking place, then slowly the reaction rate is going down. So, by these equations we can easily understand that what is the thin film growth rate onto the substrate itself. So, here we are giving one example of the growth rate mechanisms of thin films, so by the CVD methods, means chemical vapor deposition methods. So, here we are explored the CVD mechanisms using graphene growth on nickel thin film. So, graphene synthesis is conducted in two essential steps. One is called the carbon diffusivity methods, another one is called the carbon precipitation methods. So, first one is called the carbon diffusivity methods. So, carbon atoms are catalytically produced by methane decomposition process that occurs on nickel surface at high temperatures. Methane decomposition is generally described by the following chemical reactions: methane into the gas form, it is divided into the hydrogen and into the carbon. So, that carbon it is creating some kind of layer, then which is forming the graphene. So, the diffusion coefficient of carbon atoms in nickel is D is equal to D0 exponential into minus ED by Kt in centimeter square per second, where D0 is nothing but the 2.4248 centimeter square per second and entropic prefactor. ED is the diffusion activation energy, that is 1.74 electron volt. R is the gas constant, that is equal to 8.31 joule per mole Kelvin. So, by knowing this one we can easily calculate the diffusion coefficient of the carbon atoms. So, here this is the whole schematic diagram that how we are forming the graphene. So, we are having that nickel, so which is having the 200 nanometer thickness, we are heating that materials, then simply we are purging the methane gas inside the chamber. So, when this methane gas is coming with the nickel, simple it is forming some kind of carbon atoms onto the substrate itself, then this carbon atoms is going inside the nickel wafer, okay, or maybe that substrate onto the nickel wafer itself. So, carbon another process is known as the carbon precipitation process. So, where during the cooling period carbon atoms precipitation on nickel surface occurs due to super saturations of the diluted carbon in the nickel metals. So, process nickel films are most fast annealed in argon hydrogen atmosphere at 900 to 1000 degree centigrade to increase the grain size. Then exposed to hydrogen and methane gas mixture, hydrocarbon decomposes and carbon atoms dissolves into the nickel film to form a solid solutions. Finally, samples are cooled down in argon gas. During the cooling down process, carbon atoms diffuse out from the nickel carbon solid solutions and precipitate on the nickel surface to form the graphene films. So, actually the thing is that first we are taking the nickel substrate, then we are purging the methane gas, then some kind of atoms it is forming, it is going inside the nickel materials, then when we are cooling that material, simply that molecules is nickel carbon molecules, it is directly coming and then carbon is substrating, or maybe the graphene is depositing onto the nickel surface itself. So, here the carbon precipitate on nickel surface while cooling. So, whatever the nickel carbon atoms it went inside. So, simply it is coming and it is depositing onto the surface of that nickel foam nickel substrate, and then it is forming the graphene structure over there. So, graphene growth rate affected by the quality and continuity of the graphene film could be affected by numerous CVD parameters such as temperature, hydrocarbon means what are the CH4 means methane concentrations, hydrocarbon pressures and the cooling rate. Graphene growth mechanisms is significantly affected by catalyst type, structure quality and the carbon solubility. So, these all are the important input parameters by which we can control the growth rate of the graphene onto the nickel substrate. Assumptions for explain the mechanism growth: carbon atoms diffusions via grain boundaries is very negligible. Carbon atoms are uniformly distributed in the nickel film during the annealing stage. Precipitate carbon atoms are homogeneously segregated and distributed on the nickel film surface during cooling period. No carbides in the nickel films are the formed. So, these all are the different types of assumptions based on the experimental results. So, now we are coming into the conclusions that we have in this particular module we have discussed various gas phase techniques such as CVD, ALD, thermal oxidations, thermal nitrizations and molecular beam epitaxy. Some of the topic like CVD, ALD we have already discussed in our earlier lecture, and in this particular lecture we have briefly discussed about the thermal nitrizations, molecular beam epitaxy, thermal oxidations. They provide high quality thin films using gas phase as a precursor, because our main motto of this particular module is to see that how we can deposit the thin film onto the substrate itself. Thin film deposition rate is highly dependent on temperature. Obtained high quality thin films can be used in semiconductor based electronic device fabrications. So, already we have discussed all this in this particular lecture. Thank you.